Welcome to the pre-recording of the first half of Lecture 3 of Computer Algorithms 1 in the 8-week summer. This is the third lecture in an 8-week course which runs twice as fast. It is on a Friday, so at the end of the first week, so we have reached an important milestone at the end of this lecture. This course builds on data structures. In the previous lecture, we considered efficient algorithms and the big O, big omega, big theta notations. We also stated that the Gale-Shapley algorithm takes a number of iterations that is quadratic in the input dimension. That doesn't mean yet that the algorithm itself is having a quadratic running time, because we have not yet stated what the primitive operations are on the data structures. So that is actually what we mean by implementing algorithms in this course. So in the second part of this lecture, which will be the next pre-recording, we will consider graph traversals. Okay, what do we actually mean by implementing algorithms? So there is this famous book by also this famous author Niklaus Wirth, who stated algorithms plus data structures equals programs. So that's when I was an undergraduate, we studied this book. So in this course, programs are actually not really considered. This is not a coding class. We do the design and analysis of algorithm. But still, we talk about implementing an algorithm. So when we talk about running times, all the running times are expressed in the primitive operations that are executed. So we say that an efficient algorithm runs in polynomial where the number of primitive operations, primitive means that can be executed in constant time, these are the primitives, that is bounded by a polynomial. So by just counting the offers in the Gale-Shapley algorithm, we have shown that there could be no more than n square offers, which is the bound on the total set of pairs of employers and applicants. Now, that's not yet imply that the running time of the Gale-Shapley algorithm is of order n square, because we have to make sure that every iteration can be executed in constant time. Now, rather, because we are now following we have mastered the big O notation, so we like to use this. Constant time, we could say just it's a constant, but we denote this here by O of 1. O of 1 is anything that can be bounded by some constant. And that constant can be very large. So for practical purposes, constants do matter. In the asymptotic analysis, they do not matter. All right, let us review the most common data structures. So we will be using arrays. So what is typical for an array? All data elements are of the same type, so it is very efficiently for the computer to locate every element. So that was the practical definition. So here you see that the main property for arrays as far as cost goes, that getting access to the ith element is a constant time. And here we deal with integers. An array which stores 3, 5, 4 is just depicted as 3, 5, 4, putting them in boxes. Last last lecture 2, we considered binary search as the first example of an algorithm which runs in sublinear time. Um, Very important. So this indicates the importance of sorting algorithm. Now, um, prove actually here that binary search on an array runs in sublinear time. So we have given in the previous lecture the proof by induction on merge sort. You can do something similar here. Because we are using the fact that we are working on an array, so accessing, say, the middle element can be done in constant time. So that is a statement that you must make in the solution of that exercise. So that is a primitive operation, runs in constant time, locating the middle element of an array. Okay, two-dimensional arrays. So in the Gale-Shapley algorithm, we have preferences for every employer. There is a table of preferences, and for every applicant has also ranked the preferences of the employers. So here you see an example of a matrix. So a matrix is represented as an array of references to arrays. If we are using the Python terminology, we could also say that it's an array of pointers. So you can see it's a two-dimensional data structure. So we have the beginning of each array of each row in the matrix. Also here, very important, the bottom line of this slide, if you have an array, one sees the pointers, but still the cost of accessing, say, the element on the second row, first column, we are doing two accesses in two matrices, and accessing in an array is constant time. So twice times a constant, so we don't write 2, we just write the O of 1. It's just a constant. Okay, linked lists. Linked lists have the virtue that they are dynamic data structures. So with an array and a matrix, you have to know in advance how many elements you're going to need. With the linked list, this is not the case. And here you see an example of how we store the data 3, 5, 4, these three integers in a linked list. So we have a head node. So the linked lists points to the head node, and the head node contains two fields, the data element at the first position and a pointer to the next node. The last node has the null pointer as the value for the field next. Okay, so one can have circular lists. This is often very useful in implementing waiting lists. So you have a capacity, a fixed capacity, fixed number of seats, and imagine a circular waiting room. If you visit the doctor's office or dentist's office, then the next person in the circle is actually the next current person to be served. So this is also therefore important about orders. So circular lists might be important when the first element actually doesn't really matter. There's not really a first. The first actually may vary. Then here you see the example of a circular list. Doubly linked lists have the advantage that traversing from left to right, from head to tail, and from tail to head is very efficient at the expense of extra data. So you need to store twice as many pointers as a singly linked list. Here you see the two null values. One can link the first null value to the last node and the last null value to the head node. In that sense, then the doubly linked list becomes circular. Okay, time for the next exercise because we're starting to feel rather board because this is something that we have covered in data structures. Well, why does this matter for this course? Well, if you are manipulate a linked list, um, I said the main advantage is that you can um, add, um, you can, you don't need to fix in advance the number of elements. So that has a drawback. So the cost to locate an element in the list is depending on the size. So it's a similar algorithm of locating an element in an unsorted list, for example. Now the point of this slide is actually that the cost of updating is constant. And that is independent on the size of the list. So you can demonstrate when you solve this exercise, you can demonstrate the steps in the algorithm on a list of 3 elements. That's perfectly fine, but you have to make sure that you indicate that you have a constant number of steps. So what this exercise invites you to do is to dust off your textbooks on data structures and go through the algorithms for inserting and deleting a node. Whether the node is the first node, the last node, you assume that you have a pointer to that node. So there are 2 statements here. If you insert in front of the list, you have already the pointer of the list, or you have the pointer to the current node where you insert. We have a doubly linked list. If you have a singly linked list, then you have to work with 2 chasing pointers to the current and to the previous element. With a doubly linked list, it's a little bit more easier. You don't have two consecutive pointers on input. So you have the current position given, and you want to delete the current node. You have to adjust the pointers to the previous node and to the next node. The point is that there are a finite number of primitive instructions that need to be done. So you have a finite number of assignments of pointers, which are integers, by the way. And that is independent of the size of the list. Okay, so that was what we needed from data structures for today. So I will go over the Gale-Shapley algorithm again to make this lecture self-contained. So we have started this course with the Gale-Shapley algorithm. So we want to match employers and applicants. Every employer has one job opening. Every applicant works for only one employer. So we have this N to one-to-one mapping, and we have as many employers as we have applicants. So there are two tables. One table with the preferences for the employers. So the employers have ranked the applicants, and also the applicants have preferences for whom they want to work. So the dimension of the problem is the number of employers and the number of applicants. In the previous lecture, we have stated that the input size is twice n square, where n is the number of employers. How do we store the input data? Well, we know the number of employers and applicants in advance. So a matrix is the typical way to represent this. So here you see the example. We have 4 employers, 4 applicants. So we have a 4 by 4 matrix stored as an array of pointers to arrays. So we can use, so I used letters for the applicants, but actually also for the applicants we could also index them with numbers. So in the general notation we were using E1, E2 up to En. So the index is actually here identified with the employer. So where we write E is the name of the employer, but what is implied in our notation is that we take the index of the employer. The same for the applicant. Okay, how did the algorithm work? Well, the algorithm computes a set of pairs, pairing one employer to one applicant. So this is the set of committed pairs. The data structures, when we first formulated the algorithm, were actually accessed through queries. Throughout the algorithm, we wanted to query, we want to ask whether an employer is still uncommitted, is still free, and whether an applicant is still free or not. And we had also a similar function. So symbolically, we can store data in function. We still have functions that store the offers. So we had the convention that any employer does offer only once to the same applicant. So employers can make many offers to applicants, but they all have to be different. So once an applicant turns an employer down, that applicant never receives an offer anymore. Employers make offers in the order of the preferences. And here we have the initializations. So then the algorithm is actually very simple to state. There are 3 steps. There is an exit condition after the first step. So we exit if there is no applicant left for a free employer to make an offer to. We have demonstrated that when the algorithm terminates, we have a perfect matching. So the second step is when an employer decides to who make an offer, and there is still a typo here. So this should be an A, not a W. So there is the stable marriage problem as well, and you can read about this in the textbook. So in the second, once the second step is done, there will be an offer made. So we record that an offer will be made. Now, if the applicant is uncommitted, then the applicant has no choice but to accept the offer. So we are then also adjusting the data structures, uh, adjusting the outcome of the queries. Both employer and applicant are committed in that case. In the other case, the applicant has a choice. So the applicant is committed. So the else case now, the applicant is already committed, but the applicant will break the commitment to this E prime here in the notation if E prime is lower in the preference list than E. So you can see here we then break the commitment, we remove a pair, and then we add a pair. So this also kind of ensures that every applicant will be committed to only one employer. Okay, so I went a little bit slow over this to make the lecture self-contained, but we went over this in great detail in the first lecture. Okay, so let's see. So how are we going to take care of um, the data structures here? So we are using we have to look at the first statement here. We have to decide whether an employer is free or not. So we will store the set of free employers. So that's actually what determines the next step. So in every step, we need to select an employer. So we will actually work a linked list. So the next free employer, so we have the employer simply ranked, and we will go through that list. So now you see it's very important that we made the exercise on the linked lists. So we will pop from the list, the front from the list, so to get the next free employer. And if an offer is accepted, the employer becomes committed, no longer free, then we also have to delete it. So this is when the popping happens. So it was a little bit too fast. So we first locate the next free employer, and then we delete the first element. Now it could be that an employer becomes free again. So this happens to this employer E prime in the algorithm, and then that E prime will be inserted to the front of the list. Okay, so as far as the data structures go, so as far as executing that very first let E be a free employer, that very first line in the algorithm, that can be done in constant time. However, the initialization takes linear time, linear in the number of employers. But that will be fine because the total cost is n square. Okay. So we are making offers in the ranking. So orders are being made in the order of the preferences. So how do we, so we also have to do the has offered there. We can actually store this by a pointer. So for every employer, we have this next pointer, which points to the first element in the array of applicants, or it's actually an index. It's an index to the next employer to which to offer. So here in this example, so it's best to look at the example. So for employer, the second employer, the next employer is the third one on the list. So the employer has already offered to 2 and 1. So has already made a job proposal to 2 and 1. So the next time that the employer needs to make an offer or becomes free, it will be done to 4. So next is just an array. So for every employer, we will have a list of a sequence, an array of indices. And that actually also takes care of the has offered function. So we actually know how to pick the applicant to which there has not yet been made an offer. Okay, storing the commitment. So as soon as an offer is made, then we just increment the index. So in this next, we go to the next one. Okay, this is for the employer. So we actually have then stored the commitments. We actually can actually also see to who the offers were made via this next index. Okay, we need to know now for the applicants, are they committed or not? We're going to use an array, and in some sense, why not use the linked list? Well, remember that the situation for the applicants is different than the employers. Employers may become free when an applicant breaks the commitment in favor of a higher ranked employer who makes an offer to that applicant. Now, applicants actually also always, once they have accepted an offer, they may switch employer, but they remain committed. Uh, so actually, so the sequence of applicants, so we can actually store this with uh, an array. And what this array will do, it will serve two purposes. It will serve the purpose whether an applicant is free or not, or it can also be used to look up for every applicant to who the applicant is committed. So in some sense, it also gives us the structure for the output. Okay, working with arrays, we started with that. That is easy. So everything is constant time. So the is free on an applicant, this function can also be implemented in constant time. Okay, we were already at step 3 in the algorithm. So that's now we come at the last step. So we have to compare rankings. And we have to do this also in constant time. So we have to, when there is an offer coming in and to a committed applicant, the applicant wants to check very quickly whether it is worth considering that offer. So we are going to check, so again, the is free. So the if statement, whether you are in the if the applicant is committed or not committed, or engaged, if you like, then we are checking that current data structure. Now, for the preferences, we need additional data structure, and that is called the ranking. So we need to decide if an applicant prefers the current employer over the employer to which an offer comes, from which an offer comes. Okay. How does this ranking work? So this is an auxiliary data structure that is necessary to make that test quickly. So the ranking, so if we have the preferences, then with the ranking, we decide the position of the employer in the ranking. So I should have emphasized this on the previous slide. So we are implementing the preferences. So this is actually this statement here. We are implementing this statement. So this statement here in the algorithm. We are implementing this via this ranking. So the ranking determines the order in the preference list. So, and for any employer, for any applicant, we need to check this in constant time. So this is a lookup in an array. So from the preferences, we determine the ranking. So, so here we have the preferences for the applicants, and you can see that the preference list is constructed going through the ranks. So we have the elements. So if you look here, the second employer is the first choice for the first applicant. Well, that will come first. So for applicant 1, at the first rank, we will indicate that at the position 2 in this ranking, we will put the ranking 1 because applicant 2 is ranked first. Okay, saying in words make it look very complicated. We have now another initialization cost. So I think that it should be now clear by now that all the steps in the algorithm take constant time at the expense of an initialization and an additional data structure. So we have actually increased the space by n square. That the cost of the initialization is n square will not do anything to the total running time of the algorithm. Okay, we are almost there, and I'm almost at more than half of the pre-recording, so everything is running fine. So what do we have? We have the input data structures, which we store as two matrices. We have a linked list of all free employers. At the end of this algorithm, that list will be free. Initially, it takes linear time to initialize that. We have the next array. So for every employer, we have a next array. So actually, this is again another n squared data structure that we are needing. So in some sense, the input data 2 times n squared gets doubled during the running of the program. So we have the current, which indicates for every applicant to which employer the applicant is currently committed. And then we have the ranking. Okay, I was emphasizing that the size during the running of the algorithm, if you actually really work with huge data sets, doubling the input size might not be something that you may want to do. When do we don't need rankings? We've seen a scenario, and I can already tell you in which scenario that the ranking does not matter. the preferences of the applicants do not matter if all employers have a first applicant, the highest ranked applicant for every employer is different. That's the answer there. So in some sense, this exercise is simply thinking about the initialization cost and also actually thinking about an optimization in the algorithm. Okay, running the Gale-Shapley algorithm once again. So this was exercise 2 of lecture 1. So this exercise will be collected after you have received feedback from the first exercise. So this will be collected in the next Friday. It's also important, therefore, that you do the second exercise. So here you run the Gale-Shapley algorithm again, but now actually you have to do this with the evolution of all the data structures. A little bit more cumbersome, but I think that in this way you will fully understand how the data structures work. Okay, so this exercise should actually be solved before the main result, actually the first main result of this lecture, but the main result of the first half of this pre-recording. So we do have that the running time of the Gale-Shapley algorithm is quadratic in the number of employers and the number of applicants. In the previous lecture, we stated that typically we work with the input size. So the input size is quadratic. So you would say it's linear in the input size, the capital N. But it's more naturally if you double the number of employers and applicants, your running time will actually quadruple. Okay. We look at the steps in the algorithm again. So we also have to show actually that in doing so, as a byproduct, we will show that the data that we need is also bounded by ON square. So if you have a data structure that is cubic, for example, then the running time can't be quadratic. Okay, so the initialization step, the ranking is most cumbersome. So accessing all the arrays takes constant time. So we have an other initialization. The linked list of free employers is linear in the number of employers. Now, operating on that linked list, in fact, we were always inserting to the front, which also makes it, we can work with a single linked list. That is constant. Another initialization and another data structure is the arrays next. We have the arrays next. I was probably confusing you that next is quadratic. Next is just a single one-dimensional array. For every employer, we have the index, it's just initialized to 1. So it's the highest ranked applicant that is initialized to. Current is initialized to 0. Okay, the point is from these 3 bullet points, the initialization cost is dominated by the construction of ranking, which takes n square. After that, during the running of the algorithm, every operation runs in constant time. And that was the most that we could afford, given that in the worst case scenario, n square steps in the algorithm could be done. So the algorithm actually runs in quadratic time, quadratic in the dimension of the problem. Okay, quod erat demonstrandum. So this is our first algorithm, the Gale-Shapley algorithm, that we have investigated very thoroughly. We have proven that it terminates, proven that it is correct, it gives a perfect stable matching, proven that its outcome is unique, and now we have proven that it runs in quadratic time. So in the first week, this is our first accomplishment, um, that we have analyzed one algorithm. Um, so in the so in some sense this is already a milestone. During the entire course, we will investigate many algorithms and then arrive at the theory of NP completeness. Okay, that is the first half of lecture 3 on implementing algorithms for which data structures are critical. And implementing is here by assessing what is the cost to access and initialize the data structures. In the second half, we will investigate graph traversals.